So on Tuesday, here's where we left off. We figured out some stuff. We figured out that, that if acceleration is constant, we have a bunch of equations that we can use to evaluate the motion of an object. And there's some things about this that are important to note. The first is, these equations only work when acceleration is constant. They're only predicted when acceleration is constant. If I give you information about an object that's moving without constant acceleration, then you might be able to put that information into these equations and get a number out of these equations, but that number won't be predicted. If there's a bee, a bumblebee, that's buzzing around and it doesn't have constant acceleration, and you know that it started at this speed, it went this far, and at some instant its acceleration was some value, you aren't going to be able to use that to predict how fast it's going to be going later. You can plug the numbers in, you'll get an answer. That won't match what the bumblebee is actually doing because the bumblebee isn't moving with constant acceleration. So that's the first key thing to understand about these equations. The second key thing is that all of the equations that have a t in it, those equations all are actually using the change in time, delta t. It's not what time the stopwatch says that determines how fast something is going. It's how long it's been moving with constant acceleration. So if something is moving around and you're timing it, and in 2 seconds it begins moving with constant acceleration and you know some stuff about it, and then at 7 seconds you want to know something about it and you want to make a prediction given constant acceleration, from 2 to 7 seconds is a change in time of 5 seconds. So our t in that case would be 5. It's not what the stopwatch says, it's how much time has elapsed. This is a physics shorthand that many people use, including me. It's not my idea, but we've got to be aware of that. There are going to be times when this t does mean final time. Not in these equations, but in other equations or other examples. And so we just have to be really aware of what, what that t stands for. Then the last thing, and I didn't talk too much about this on Tuesday, but the last thing is these equations are all set up so that they kind of look like you're getting something, like there's some sort of typical thing you're looking for. Like an object's final position. If you know all this stuff, you can find it. An object's final velocity. If you know all this stuff, you can find it. The square of an object's final velocity, which seems like kind of a stupid thing to find, but I guess if you take the square root of it, that might be useful. You can find if you know all this stuff. And an object's average velocity, if you know all this stuff. And as it turns out, I mean, that's true, of course, but as it turns out mathematically, with any one of these equations, if you have one unknown, you can find it algebraically. That means if I know an object's final position and its initial position, its initial velocity, its constant acceleration, I can find how long it's been moving. That information is enough for me to calculate the amount of time that it's been moving. And yeah, this is complicated because it's got some squares in it, t squared and t, and so you would use the quadratic formula at least sometimes, but it works. So you can find the amount of time an object has been moving from this equation. And that ends up being handy because you can find a bunch of stuff. If I need to know an object's acceleration, I can find it, right? If I rearrange this equation algebraically to solve for acceleration, then so long as I know its displacement, its initial velocity, and its final velocity, I can calculate acceleration. That's great. But it also is confusing because you realize, well, acceleration shows up in all 3 of these. And initial position shows up in 3 of these. And final velocity shows up in 3 of these. 1, 2, 3. So how do you know which one to use? If you have a math problem and the math problem says, what is the final velocity of the wagon, then you go to your list of equations and you find the one that says final velocity equals something. But what do you do in this case when we have final velocity equals this? We can use this to find final velocity. We could also use this to find final velocity. And I'm going to show you a system for working backwards to figure that out. This isn't like math. It's not find the equation to get the variable you want. It's figure out what variables you have, and then determine what equations you can use. Sometimes you can't even get the right answer right away. Sometimes you have to do multiple steps, and you'll see that today. Okay, so our work today is going to be centered around trying to kind of nail down how to solve problems. And where we're really going with this is we want to be able to make predictions of real things. So the problems that we get on paper in the book, examples that I give you in class, are all going to be the kinds of things where conceivably you could take some measurements and use those measurements to calculate some values, and then use those values to make a prediction of a real thing, like a cart rolling down a track or a projectile launcher. Okay? So I'm going to start with a couple of things that are really, they're important to know, and they're related to solving these problems, and they're really what I think of as like hidden values in physics problems. So a lot of times in physics, we're dealing with objects that are just like in the air. So, you know, a rock that's being thrown, or you know, somebody jumps off a high dive. Those are all examples of problems where something is in the air, moving through the air, and there's not really anything else affecting it, right? It's just, you're just in the air. And the only thing that's really working on you is the Earth's gravity. And that situation is called free fall. Free fall is when an object is unsupported by anything. And free fall, really, we only think about free fall in objects that are sort of close to the Earth. It turns out that the farther away you get, the more things kind of change. But if you're close to Earth, if you're anywhere near the Earth's surface, and nothing is holding you up, then you are considered to be in free fall. And that goes for people, and that goes for objects as well. So if I take this ball and I throw it, as soon as it leaves my hand, it's in free fall. If I drop it, as soon as it leaves my hand, it's in free fall. There's a whole bunch of ways that this thing can be in free fall. I could throw it sideways, it's in free fall. Some things that are in free fall are a little tricky to work with, because we want to be able to make predictions, right? But if I take this plastic bag, if I want to throw this plastic bag, like if I wanted to hit that computer sitting there, I could throw it, but it doesn't go where I expect. And the reason for that is because this plastic bag isn't a real good free fall thing, because it's light and it's kind of big, and so it actually is sort of supported. It's supported by the air, and it's slowed down by the air. So that, we would still probably call it free fall, but it's not really, we can't really make predictions about that. If you tell me there's a slightly wadded up piece of Kleenex and you drop it from the top of a building, I can't tell you how long it's going to take to hit the ground. On a windy day, it could take several minutes. But most things that are reasonably small and have a reasonable amount of mass will exhibit free fall acceleration. And in free fall acceleration, an object will speed up towards the ground at 9.8 meters per second per second. So usually, not always, down is negative. And that means that in free fall, acceleration would be negative 9.8 meters per second squared. You can't count on that. If somebody gives you a problem and they say, what's the acceleration, and it's in free fall, you can't necessarily say it's negative 9.8 meters per second squared, because down might be the negative direction. But usually, up is positive. In the book, up is always positive. In many, like, it's sort of like user choice. So on the AP exam, up is typically going to be positive, but they have the right to say that down is positive, so you can never know for sure. I'm never going to try to fool you. I'm never going to give you a problem where down is positive, omit that information, and then try to trip you up. But there will be times when I tell you down is positive for whatever reason. If I want to just work with positive numbers and forget about negatives, I may say something starts here, call that position 0, call my downward direction positive, and then as it moves down in the positive direction, we would measure its location relative to that original point. That's reasonable, and people do that relatively frequently. If you have an acceleration, now let's say if down is negative, so if down is negative, and we think about an object's velocity versus time, then the velocity is always going to be becoming more negative. So whatever the velocity starts at, as time goes by, it will become more negative. And what's interesting about this is the motion we see will depend on the direction of the initial velocity. The easiest case to think about is this one, where we take an object, we just drop it. As soon as I let go of it, for just an instant, its velocity is 0. Okay? So if I drop something, then its velocity versus time graph is going to look like this. It's going to start at 0, and it's going to become more and more negative as it speeds up on the way down. But what if I give it a little throw? What if I throw it down? Then, at the instant it leaves my hand, it's already moving. And if that's true, then my velocity versus time graph looks more like this. I'm throwing it downwards, and that means that it starts off moving in the negative direction, and then it speeds up because it's in free fall. The most complicated one looks like this, and this is the case where something is thrown upwards. And that is this case. And what's going on there is it starts with a positive velocity. It's moving up. But that positive velocity is becoming more and more negative, which means it's getting closer and closer to 0, which means it's slowing down. There's an instant where it's motionless, and then it starts becoming more and more negative in velocity, but since its velocity was 0, now it's speeding up as it falls. When you throw something up in the air, as soon as it leaves your hand, it starts accelerating downward at 9.8 meters per second squared. And until something else touches it, it will continue to accelerate downward at 9.8 meters per second squared. It looks very different because it's moving up. Moving up, accelerating down, that's an interesting condition to think about. That means that you have velocity that's positive and acceleration that's negative. And that ends up playing out like this. It will slow down and then reverse direction and fall back down toward the ground. Okay. And there are, let's see, there's a couple other things that I want to show you that fall under this category of hidden values. And this stuff, so this is going to be a lot, and I don't expect you to write this down. But these are things that you can sort of file away for future reference. One is, based on what we just said, you could figure this out, that when an object is thrown into the air, when it's at its highest point, its velocity has to be 0. And you know that because if you go from a positive to a negative velocity, your velocity graph has to cross the x-axis. There has to be an instant in time in which your velocity is 0. That happens if you throw something straight up in the air. That happens if you throw something in an arc. At its highest point, its up and down velocity is 0. That happens when things change direction, even if they're moving horizontally. So if I were to take this cart, for example, and roll it up the ramp, at that highest point, its velocity was 0. And then right here, velocity 0. And here. Every time it reverses direction, it's instantaneously motionless. When things are moving, like accelerating quickly, we don't notice it. It looks like this fluid motion. And in fact, if we were try to measure the length of time that this thing was moving with no velocity, that amount of time is infinitely small. But it has to be true. So that means sometimes we know the velocity, even though it's not said in a problem, right? It may be 0. Another hidden value is that sometimes we're gonna have a couple things in a problem, and we're gonna be told like where they are, how fast they're going, and those are 2 separate objects. We have all the variables that we're talking about, velocity and position and acceleration, but if you have 2 objects, they may have different positions at different velocities, even different accelerations. If they're both in free fall, they won't have different accelerations, but if they're not in free fall, they may not. This kind of problem is often presented as like the sort of the canonical physics problem is that a person on a bicycle is riding with a constant speed and somebody on a motorcycle is accelerating. The bicycle goes by the motorcycle, it's almost always a police officer, right? The bicycle goes by the police officer, and the police officer turns on the siren, starts accelerating at a constant rate, and what you want to know is when are they going to catch up to each other? Or at what point are they going to be going the same speed? And so to think about a problem like that, we have to recognize that each of our objects has its own set of variables. And sometimes we can relate them, like if they are in the same spot, then they would have the same x values, right? The same position value. Or if they have the same velocity, then their velocity at that time would be the same. And then the last thing, just to reinforce this idea, is that our t variable in our equations is not the time that your stopwatch says. It's the amount of time that has gone by since the object had one position and then a different position, or one velocity and then a different velocity. The things that are changing change over time. The t variable in the equations that we're using reflect that change in time. It's not what your watch says, it's how much time went by, okay? So with all that in mind, I'm gonna show you my framework for problem solving, and then I'm gonna solve a problem for you, because it's gonna be good for you to watch whether or not it's something that you can easily keep up with. So, so here is how I'm gonna deal with these kinematic problems, okay? The first thing is whatever the situation, whether it's real life, or whether it's a problem in a book, or whether it's a question that one of you asks me, I'm gonna draw a picture. And after I draw the picture, oh, hang on, you don't have to write this down, by the way. You don't have to memorize this. If you ever need it, you can look it up, and I will give it to you if you need. Like, I have equation sheets where I have that written on there, like this one right here. This is for forces, but I'll give you this stuff. You don't have to memorize this or write it down, but I want you to be able to use this. And more importantly, I want you to be able to use this to communicate to me. So if you show me work that you've done, and I don't see any of this stuff, I might not be able to figure it out. If I can figure it out, great. You don't have to do it my way. But if I can't figure it out, then what I'm gonna say is, go do it my way. Because otherwise I just simply won't be able to understand you. So, so that's, and then the other thing to think about here is that many of you will have to do this in order to solve the problems. Some of you won't, but many of you will. If you don't follow these steps, you'll get stuck every single time. So I came up with this not for me. I came up with this because what I noticed is if people do this stuff, then they can get the answer. If they don't follow these steps, they often start here. What am I trying to find? Final velocity? Okay, final velocity equals initial velocity plus acceleration times time. What's the acceleration? It's negative 9.8. How much time? We don't know. Oh crap, I have 2 unknowns. I can't solve the problem. Brigar, how do I do this? And the answer is, draw a picture, which is the first step. So you draw a picture, and then on your picture, you need to tell me where 0 is. And if we're working in 2 dimensions, which we'll start to do next week, then you need to show me where 0 in each dimension is located, the origin. And then tell me which directions are positive. For objects that are moving in a standard coordinate plane where horizontal and vertical are what we're thinking about, then typically to the right and up will be positive, but not always. And then this step here, we don't have to worry about until next week. This step has to do with what happens if we have something that isn't moving in the direction of our axis. So if we, for example, had a cart that was rolling down this ramp, and then it got to a certain point and it hit a rough spot and it jumped. And now all of a sudden it's going kind of, it makes a little parabola, right? Like Dukes of Hazzard. So at that point, it's no longer moving in one dimension or the other dimension, but we have to think about its motion in both dimensions. So we're going to use some mathematical tricks to do that I'll show you next week. The next step is to figure out, based on the information in the problem and some of those like hidden values, what is our like set of variables that are known. And typically we'll know many, but not all of them. And often there'll be at least two that are unknown. But from the information in the problems, we'll be able to find more information. From that information, we'll be able to get what we want to know. And then the last step is, which equation do you use? And the answer to that is, it's not use the equation that gives you the answer. It's use whatever equation you can. Sometimes you'll get the answer by doing that. But often, you will have a set of information and you'll use it to find something. Once you know that thing, then you'll be able to find the answer. And I'll show you an example of that in just a second. And then some things to think about in the book and on the AP test and like in real life outside of this classroom, you just never know what people are going to do with units. Okay? And many of you have probably heard the story about the NASA spacecraft that was launched and it like went up in flames because some of the engineers were using the metric system and some were using the imperial system and they didn't communicate about it. And so they were just like, some people thought that the 3 was meters and other people were like, that 3 is feet, and it didn't work at all and they lost like billions of dollars. And that's important. So, you know, working for an engineering company, like that's worth keeping in mind. But honestly, mostly when that comes up in a classroom, it's your teacher trying to trick you. Or if it shows up in a book, it's the book trying to trick you. And I don't want to try to trick you. That's not the point of the work that we're doing. So I'm going to try to keep the unit straight. It's always a good idea to double check, but I don't really care if you like flub up with the units because somebody measures something in feet and you assume it's meters. I couldn't care less. Okay. And then this piece right here is important. You need to check for constant acceleration because it's very common, and you'll see an example of this in just a second, that the description of a scenario will involve 2 time periods during which there are different but constant accelerations. You can't use those equations over the whole time period because the acceleration isn't constant. So you use them over one time period when the acceleration is the same, and then when the acceleration changes, you use them over another time period. That is super common. And then you will not need to break things into 2 dimensions of needed, but we will next week, so we won't need to do that today. And then sometimes we're gonna have to like break things into parts, find one thing first and then find another thing and then use that to find some third thing. Like in real physics, that's what it actually looks like. In real physics, it's this complicated cascade of finding unknowns until you finally end up with one that you want. In this class, it's typically going to be like 2 to 3 steps at the most, but that's potentially going to be part of the show. So I'm going to show you an example of this, and what I want you to see here, a couple of things that I want you to see. Number one, this is kind of this is going to be aligned with the work that we do in 2 ways. Okay, one way is sometimes we're going to need to do something like this to make some initial measurement. Like when we launch a ball from the projectile launcher, we may need to make some measurements so that we know how fast it's going when it comes out of the launcher. That is kind of an important thing to know. And then, once we know how fast it's coming out of the launcher, we could use that to make some other predictions. The predictions that we make, the measurements that we make, will often involve solving kinematics problems. If I roll a cart down a ramp and all I have is a stopwatch and a meter stick, I can tell you what its acceleration is. I will use kinematic equations to do it, and you'll be able to do it too. I'm going to teach you how to do it, so everybody here will be in the same position. Some other things to think about. First, this problem here is asking about a model rocket launched from the ground with an upward acceleration of 2.0 meters per second squared from rest. Its engines turn off at 150 meters. And this I stole from a book called 5 Steps to a 5. And in that book, they only ask this question: how long will it take to come back to the ground after the engine stop? For this example, I broke it into 2 parts for you, because if it is accelerating up at 2.0 meters per second squared, it's not in free fall. The engine is pushing on it. The rocket is being pushed upward by the force of the exhaust that is pushing on the rocket as it's expelled from the rocket. That is one constant acceleration. As soon as those engines shut off, it's unsupported near the surface of the Earth. It's in free fall. We have 2 time periods here. They both have constant acceleration, but they don't have the same constant acceleration. So there's 2 parts to this problem. I broke it up for you so you could see how that plays out. And then the last thing that I'm going to say here is I'm just going to point out, I'm going to do this fast. And what I hope is that everybody here is like, okay, that makes sense, that makes sense, that makes sense. And then remember, when you get home and you work on the homework over the next few days, or you look at AP problems, or you are trying to do stuff in class, it may not be so easy. And that's okay. It takes time and practice to get there. I'm going to go quickly, because what I want to do is just model for you what it looks like from start to finish, okay? So here's what I'm going to do. Start with step 1, I'm going to draw a picture. That looks like a rocket to me, and this rocket starts on the ground. It's launched straight up. Its initial speed is 0 meters per second. It is accelerating at 2.0 meters per second in the upward direction, and there's a point at which its engines shut off, and that point is when it's 150 meters above the ground. And the question is, what's its velocity? The engines shut off, but it doesn't stop moving. It's still going up. It was accelerating at 2.0 meters per second squared for some amount of time. It sped up. It was going faster and faster and faster and faster, and when those engines shut off, it was at its maximum speed. So this is still going up. We just don't know how fast, okay? That's part of step 1. The other part of step 1 is I need to figure out where my position 0 is. Makes sense for that to be the ground in this case. And I need to know what my positive direction is. And I'm going to say that positive is up. So down is going to be negative. So that means my acceleration is going to be positive. My initial velocity is going to be positive. My final position is going to be positive. And I already know my final velocity is going to be positive too. This thing's still going up when those engines shut off. That's the positive direction, okay? So that's step 1. Step 2, I make a list of the variables. And I'm going to do this the same way every time. I'm going to list off initial and final position, initial and final velocity, acceleration, and time. You should do it this way too for maximum clarity. I had a student once, like one of the neatest people I've ever worked with, who just used weird symbols for all this stuff, like smiley face and squiggly hair guy. And that worked for that student. I couldn't understand what they were doing, so it eventually fell apart because I couldn't understand it work. So don't confuse me. And I don't say that like I'm not gonna like put my foot down and scream at you or anything, because I don't care about that kind of stuff. But if I can't understand it, it's not really evidence of what you know or can do. All right, so let's see. We know that this starts on the ground, and we define that as position 0. We know that at the moment the engines shut off, it's 150 meters above the ground. That's the positive direction. So that is position 150 relative to 0 in the positive direction. Its initial velocity, we're told, is 0 meters per second. Its final velocity, we don't know. That's what we're trying to find out. The acceleration, it's not in free fall. The engines are pushing it. Its acceleration is up, which is positive, 2.0 meters per second, and we're not told how long it's moving. So this is where it gets kind of interesting, because if you want to know what its final velocity is, many of you would go to, and I really hope this works, it didn't work in first period because, okay. You might go down this list and be like, oh, well, there's final velocity right there. It's initial position, which I know, plus acceleration, which I know, times time. That's easy. But if you go back to that problem, you realize you don't have time. This equation isn't going to help you. This equation isn't going to help you either, because you don't have time, and this one doesn't even have final velocity in it. But this one does. This one has final velocity, initial velocity, which we know, acceleration, which we know, and final and initial position, which we know. That's the equation we're going to use. Sorry, there's probably a better way to do this, but I don't know what it is. So the equation we're going to use is that third one. The final velocity squared is going to be equal to the initial velocity squared plus 2 times the acceleration times the displacement. And in this case, the variable we're looking for is final velocity, so we just take the square root of both sides. And we know, because of like our square root rules, that that number mathematically could be positive or negative, but since we know that this thing is moving up when the engine's shut off, we know that our final velocity is positive, so we don't have to, we know what the correct solution is going to be. Our initial velocity is 0. Our acceleration is 2 meters per second. Our displacement is 150 meters. 150 minus 0 is just 150. And notice I don't put the units in. Once I put my numbers into the equations, I leave the units out. It's easier that way, believe it or not. Because the units will sometimes you'll get confused. Like meters, is it meters or is it mass? So I just leave the units out once I've made my variable inventory. So this is just going to be the square root of 600. And then, I don't know how to use this calculator. I need to get my old familiar ones back. Okay, and that is not what I just got. The square root of 600. Oh, I'm not doing this right. That's because I can't see it. Square root of 600 is about 24.5. So our final velocity is going to be about 24.5 meters per second. Okay? And again, in the original problem, that's not what the question was. The question was, how long will it take to come back to the ground after the engines stop? But in order to figure that out, we need to know how fast it's going at that moment. Okay? So let's solve the second part. Let's start with a picture. Here's my rocket. At the moment the engines stop, it is moving at 24.5 meters per second straight up. It's not going to be the case that the engine's shut off and it starts moving down. It's going to keep going up, and then it's going to come down. Its motion is going to kind of look like this, right? And then it'll end up on the ground. We know that it starts 150 meters above the ground, because that's where the engine's shut off. And we know it's in free fall. So the acceleration is going to be 9.8 meters per second squared downward. Okay? And that's all we know. So let's add our reference information. In this case, it makes sense for position 0 to still be the ground. And let's make up the positive direction. So that means it starts at position positive 150. It has an acceleration that's negative, and its initial velocity is positive. When we make the variable inventory, just put all those same variables in again. The initial position, 150 meters. The final position, 0, it's the ground. The initial velocity is 24.5 meters per second. What's the final velocity? Yeah, so most of you are thinking 0. You are right that when things land on the ground, their ultimate velocity is 0. But here's the thing. These equations only work when acceleration is constant. In this case, the acceleration is constant while it's in free fall. This set of equations doesn't govern anything that happens in the instant the rocket comes into contact with the ground. As soon as it comes into contact with the ground, it's no longer in free fall. The acceleration is no longer 9.8 meters per second squared down, and we can't use our equations. So in all of these kinds of problems, we're always going to really be thinking about its speed right before it hits the ground. Or sometimes I imagine that there's a big hole in the ground. And so it comes down and it's at ground level, but it just keeps falling because there's a big hole there. Yeah?
Where did you get the 9.8 meters per second?
That's the free fall acceleration. We know it's 9.8 because there's nothing supporting it and it's near the Earth. Nothing is holding it up, nothing is pushing it around. The only thing that's interacting with this rocket is gravity. So that means instantly downward acceleration of 9.8 meters per second squared. Yeah, great question. Okay, so we don't know what the final velocity is. We know it'll be 0, but not during the period of constant acceleration. Our acceleration, since it's in free fall, negative 9.8 meters per second squared, we don't know how long it's going to take. That's what we're trying to find. How long will it take to come back to the ground? So, same deal. If you look at the equations that were given, we have a couple with time in them, but we don't know what the final velocity is. So we can only use one of those equations, and in fact, the one we can use is this one. Final position is going to equal initial position plus initial velocity times time plus 1/2 times the acceleration times time squared. And if you wanted to algebraically solve this for time, you could. But it would be kind of a mess because it's a quadratic, so you'd have to use the quadratic formula. So the easiest way to solve the quadratic formula is to get it set up so that everything is equal to 0. So let's do that instead. Let's just put our numbers in and then solve so that we have everything on one side and 0 on the other. So our final position is 0. That's going to make it easy. Our initial position is 150. Our initial velocity is 24.5. And our acceleration is negative 9.8. So that means our quadratic equation is going to be negative 4.9 t squared plus 24.5 t plus 150 equals 0. And the quadratic formula, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So negative b, negative 24.5 plus or minus the square root of b squared, which is 24.5 squared, just square that, minus 4ac, so that's about 5 times 150. The square root of that is, so it's about 27.9, I think. So that's going to be like negative 3.4, so that's not the right root. So we'll do it the other way. So it's plus or minus, so plus, so it's going to be 24.5 plus. You get about like 8 point something, right? Seconds? You got it? You can't do that in your head? Wow. You're in high school and you can't do the quadratic formula in your head? You can't do that? I can't either. I did it earlier. Yeah, so it's about negative 3.6 seconds is one of our roots, and that one is, that represents an earlier time than where we started, and then the final time is 8.6. I swear to you all, that is the best part of my job. So it's about 8.6 seconds. And I don't need you to have the quadratic formula memorized, nor do I need you to really be able to do a lot of mental math. You'll always have resources to do this. Even on the AP exam, they'll put the quadratic formula on there. I don't think there's any questions that will require you to use it. You'll have a calculator. You don't have to know how to do that kind of stuff in your head. So, yeah.
Oh, I was gonna ask if I could take a picture of it,
Oh.
of this.
Yeah, this is gonna be posted.
Oh, okay.
Yeah, so you'll be able to get all of it, yeah. And so that's it, and I know that's a lot. This is this is a typical problem. We'll start a little easier than this, but ultimately, this is the level of problem that you all are going to be solving. So when I said by the end of the month you're going to be solving a problem where you have a projectile launcher at an angle at a height, and you're going to be able to figure out where it will land relative to a little bucket that's set on the floor. That's going to be what you do, and it's complicated, but it's all doable. Philip?
Wait, are these calculations ignoring like air resistance?
Yeah, always. So sometimes we'll factor in air resistance, but we can't yet. We don't know how. So we're assuming that these objects are small enough and heavy enough that they all just sort of fall at about the same rate, which is actually generally pretty true.
So are we ignoring like terminal velocity?
Yep. Yeah, we have to, yeah. We're assuming that things will just continue to accelerate, which we know they won't. All right, I want to show you one last thing really quickly this is just a visual demonstration that I think might be kind of handy for you to think about. So this is from a simulation, it's calculus actually, but those of you who are in pre-calc or calculus have probably figured out already, the relationship between position, velocity, and acceleration. Those are calculus relationships. So on these graphs, this top one will show position versus time. The middle one shows velocity versus time. The bottom one shows acceleration versus time. And this app allows us to adjust the velocity. We're going to make it always constant acceleration. If the acceleration is constant, the slope of the velocity versus time graph will be constant. So that might mean that we have a positive velocity. If we have a positive velocity and there's no change, then we'll have a linear increase in position and zero acceleration. If we have no velocity, the velocity is zero, that's not quite zero, is it? Then our position will stay at zero and our acceleration will be zero. If we have negative velocity, then our position will become more negative and our acceleration is still zero. But if we change the slope of our velocity graph so that it has acceleration, positive acceleration will be reflected by a horizontal line on the acceleration versus time graph that's positive, and our parabola for position will be an upwards facing curve. Depending on the initial velocity, that upwards facing curve might kind of drop down and then come back up, or it might just start going up right away. It might even be going up like there may be no point at which this object is motionless, okay? And then we can do the same thing thinking about velocities that show a negative acceleration, so a downward slope. Now we've got a constant negative acceleration. Our velocity is going to start off positive, end up negative, so our position graph is going to go up and then come back down. The steeper this line is, the steeper that change occurs. And again, it may never, like the position graph may never go up. If our initial velocity is zero, then the position versus time graph just curves down. If our initial velocity graph is negative, then our position graph curves down and it doesn't start from a zero slope. Effectively, what we're doing, for those of you who are visual and like have some spatial, like pretty good with the spatial stuff, effectively what we're doing is we have a parabola and we're just moving our coordinate axis around on the parabola for the position versus time graph. The slope of the velocity versus time graph just makes that parabola bend up, bend down, or it might be a straight line if our velocity doesn't change at all. Okay? So this is something, you can get to this, it's just a calculus graph on the PhET simulations. You can look at this if you want. No need to if you have a pretty good handle, but this is one of the skills that I have asked you to think about is, given some sort of starting position and starting velocity and a constant acceleration, what will the acceleration, velocity, and position graphs look like? So this is one way you can play around with that really easily.